Hi, everyone. My name is Rand. I'm the CEO at Zama with Pascal, my co-founder, who's also here on the call. So we've been doing those FHE.org meetups for a couple of years now to bring the community together and give everybody a chance to understand what the state of the art is in homomorphic encryption. There's still this kind of belief that FHE is far in the future, but all of us here, I think, believe that it's actually much closer than most people think. And so we're trying to make sure everybody knows that. This is a very technical meetup, so it's really meant for people who want to understand the technology behind homomorphic encryption. So if you guys are working on some really interesting research, please let us know. We'd love to have you in a future meetup. So today we're going to be talking about private information retrieval with Samir from Spiral. You probably heard about the work they've done with the Wikipedia encrypted search. I remember I saw that buzzing all over Hacker News a few months ago. That was really interesting. One of the first time the homomorphic encryption kind of went to the front page, right? So thank you for that. It gives everybody here a lot of visibility. So we run this meetups once a month. The next month's meetup is going to be about, I believe, security. Is that right, Jeremy?
Yeah, LW.
Okay.
Yeah.
All right, great. So yeah, so next month we're going to have Martin Albrecht talk about the LWE estimator, the lattice estimator now it's called, I suppose, and the security of homomorphic encryption. So Samir, I'll let you introduce yourself and take over.
Sure. Yeah. Thanks. That was very complimentary introduction. We just started this company called Spiral. We're trying to build systems that use FHE today to deliver privacy today. That's like our whole mission. Yeah, a little bit about me. I'll explain in the presentation. So let me just get my slides. So. All right. Can you see my slides?
Yeah, all good.
Awesome. Okay. So I'm Samir Menon. I'm a co-founder of Spiral Privacy, and this talk is actually going to be maybe slightly on a slightly less technical side of FHE.org talk, still pretty technical, but I want to talk, there's a lot of talks about schemes and technology. I want to talk a little bit about, kind of what does it look like to deploy this in the real world. So today we'll talk about real world deployment of FHE-based private information retrieval. So, the first thing you learn, maybe one of the first things you learn when you learn about FHE is that you can perform arbitrary computation on encrypted data. And that's kind of incredible. The fact that you can do arbitrary computation, like of any depth, just anything you can dream of computing, you can do it on encrypted data. That's, you have this incredible moment, I think, that is kind of draws you into the field and it makes you excited about it because you're like, wow, everything is possible. And not only that, but we only kind of realized everything was possible like less than 15 years ago, so it's like everything's possible recently, that's crazy. After you work with FHE maybe for some time, that everything is possible maybe trails off a bit and you go, well, everything is possible someday. In theory, you could do everything, but that is almost a crushing responsibility, a crushing weight. And what you can actually do, today with the tools we have today, kind of starts to look very sad in comparison to the dream that you had at the beginning. So in this talk today, I want to focus on what's useful today. So what can we do with FHE today that delivers privacy? And I think there are lots of cool things that we could do in the next couple years. There are lots of really cool things we could do in 10 years. What can we do today is what I want to focus on today. So a little bit about me. I'm Samir Menon. I'm a co-founder of Spiral Privacy. Company is like literally founded last week. We just quit our jobs and everything. My co-founder and I, so wish us luck, young company, etc. I co-wrote the paper that also has a scheme named Spiral in it. That's a PIR scheme, and I'll talk a little bit about what PIR is in a bit. But yeah, And before that, I worked at Yubico. And before that, I worked as a student in Dan Bonnet's lab at Stanford. And my research then was similar to now. I also did a little snark stuff, but yeah, that's who I am. So I want to talk about this problem that we're trying to solve with FHE, which is private information retrieval. I think there's been a PIR talk before at the meetup, but I'll just briefly explain what PIR is. PIR is, in some ways, one of the simplest computations you could do homomorphically. Basically, all we want is we have a client and an untrusted server, and the client just wants to retrieve a record from the server. So the server has a kind of a database of, say, n records. The client would like to retrieve record I, and the server should not learn I. It should not learn anything about which record the client retrieved. The records are in this setting plain text. So, but of course, they could be symmetrically encrypted or something like that. But yeah, for the purposes from the FHE level, the records are plain text. So, this is the FHE.org meetup. So, of course, we see this problem when we think, how can we use FHE to solve it? So, how does that look? How do we use FHE to solve PIR? I'll just give you a very kind of toy scheme that you could imagine. A toy scheme you could imagine is that the client just uploads a vector of encrypted bits, homomorphically encrypted bits, sends this to the server. The server can compute a kind of homomorphic dot product. That is, it multiplies each bit by the corresponding plaintext value and then sums all the results. And the client can retrieve the item that it wanted. So the final result will be a single ciphertext that goes back to the client. And the client then retrieves the plaintext by just decrypting. So, this is a toy scheme. So, disclaimer, there's a bunch of problems with this scheme. Obviously, the first problem is the query is the same size as the, database size. That's not good. Turns out, as you all know, you can do really cool things to compress a really long vector of zeros and ones homomorphically. So, a long line of work, including my own, has incrementally made this better and better to the point now where the queries are quite small. So even though in an asymptotic sense they're still roughly square root n, in an absolute sense they're small. So today these are tens of kilobytes and even smaller actually. So that's how we can solve PIR using FHE. But obviously the second question is why solve PIR? What's the point? So the point is PIR is such a simple problem that you can use it today to build privacy preserving systems. So we don't need to wait for big improvements. So I think for things for more complicated computations like ML, we may need to wait, or we may need to do the work of finding improvements in schemes or hardware that would enable machine learning. But today we can do PIR. The other thing is, PIR in comparison to maybe some other kinds of ways of achieving privacy in systems, we don't have a non-collusion assumption. We don't have PKI. We don't really even have the caveat that, there need to be X people using it like we would for maybe differential privacy or something. The point is, you can do this PIR thing, and the first day you set it up and the first server you get online, the client is getting full query privacy. And that's kind of cool. That's a unique feature of this single server PIR problem. There's also a bunch of applications. So, when I tell you there's, a database you can fetch records from privately, people usually start thinking of applications. One of the first ones they think of is DNS. So it would be nice if when I made a DNS query, my ISP didn't have to learn, exactly which names I'm resolving. Another one that gets more attention now, especially recently, is private block explorers. So, I would rather not just leak to a random third party who runs this block explorer what my addresses are, link that with my IP, kind of create a link between my money and my identity, even create a link between my addresses by querying them in quick succession. And then there's a bunch of other ones that are cool. I've bolded the first two because we've built systems that do that. today. The others are exciting, but we have not tried yet. So another big one is private maps. So this is like a mapping application that actually wouldn't know where you were. It's a very cool thing. I would love to see Google do it. I don't know if Google Maps will ever be private, but maybe someone will make a private map competitor. Private ads is another big one. There's a lot of research in this area. So delivering ads privately that are still targeted, but do not learn your identity. This is kind of an interesting one. So PIR also makes it easy to kind of check against a block list efficiently. So if you say have a safe browsing API like Chrome, which wants to check your URLs against a database of like known phishing sites, it would be best if Chrome didn't just have to say, here's the URL that Samir is resolving, So PIR also enables private blocklist checking like that, also for malware scanning or a gatekeeper or something like that on macOS. And then finally, I think something that definitely drew me to this field and is maybe a little further out is definitely metadata private messaging. So this is a messaging service that doesn't learn who you talk to. I think these are the things that really draw me to PIR, and the fact that it's kind of a foundational problem that can be used in a lot of different areas is what makes it exciting, and why I think I'm making a good case for looking at PIR as an FHE application. So I'll just talk about the 3 systems we built using PIR based on FHE, and I'll talk about one that we're working on now. So the 3 systems we've built are, we built a Wikipedia demo, which Rand mentioned. It was really cool. I think I was very excited to get to kind of prove the haters wrong and show that, yeah, homomorphic encryption is not this total nutcase dream. That it's real. It's here today, and you can use it. So yeah. I think this Bitcoin balance. We also built a demo that lets you look up the balance of a Bitcoin address privately. This has a lot of kind of more practical privacy concerns. I think people's Wikipedia browsing is maybe slightly less sensitive, but certainly which cryptocurrency addresses you have is really sensitive. It makes you an obvious target for phishing if I know your address and your IP. It's a really great way to say, like, rob me. So it would be great if block explorers did not learn and log all that information. So we think this is really exciting. And finally, most recently, we built a resolver for .f domains. So this is kind of like, you can think of it like mini DNS. So we're doing DNS, but on a much smaller set of names because the problem's much more feasible. But it's cool because you can actually use the browser's linking system and hashes in the URL to kind of privately send the .f domain that you want to resolve. So please check it out. I think it's really cool. As you can see, we have a domain explosion. Our registrar is probably very happy that we keep registering new domain names. We will probably consolidate at some point. But yeah, these are the 3 kind of demos that we run. We update them. I think the Wikipedia demo, the articles are a bit out of date. But the Bitcoin and ENS ones are live updating with the blockchain. So we kind of ongoing maintenance them, and we've learned something from serving these, and I'm going to share what we learned with you. The one thing we're working on that's coming soon is we kind of want to, underlying all of these systems is basically one system. It's a private key value store. So basically, at the heart of all of these is basically just a key value store where you can make a query that's private. So you can store items in it, store key value pairs, and then later you can provide a key and get an item, but the key will stay private. So you can do private retrieval. And that little primitive, we think, is really useful. And a bunch of people have asked us, can we, try that primitive? I think it's really important that we kind of provide this as a service that's easy. So we want to make like a client SDK and a service that is reliable, that kind of abstracts this for you. So even if you're not a cryptographer, you could use this private key value store to build real apps that respect privacy. So, in building these kinds of real world PIR systems, we faced a bunch of problems. I think the problems we're facing are a little new, if only because there aren't that many large scale kind of FHE deployments yet. And I'll just talk about, the problems we faced and how we dealt with them. So the first problem is that real world data is messy. So when you write a paper on PIR, you will say something like this. I know this because I said something like this. I said, our system lets you privately access 1 million records of size 20 kilobytes. So it's perfect for Wikipedia because, that's, roughly whatever. That's kind of close to the size of Wikipedia. And, 20 kilobytes sounds right. You just write the sentence in the paper and then you submit it. When you go to make the Wikipedia site, you learn some things about Wikipedia that do not match that statement. So the first obvious problem is that the articles are not all exactly 20 kilobytes. And if you think about the security model for PIR, we can't have items that are varying in size because that itself would reveal something about which items we're retrieving. So all the items have to be the same size. If you, we'll see in a bit, but if you just choose an arbitrary number like 20 kilobytes, you might waste a lot of space. So that's the first problem. The other problem is that, remember in the PIR model, we assume that the client has the index of the item they would like to retrieve in the database. On Wikipedia, when you want to look up the article on cabbage, you don't type in like 64663, right? You type in cabbage. So we have to find a way to take the title that you want and convert it into the database index. And we have to do so in a way that doesn't defeat the entire point of using PIR. So we can't just, send your query to the server, right? We need to find a way to do that privately or locally. So these two challenges, they sound kind of, I think in an academic sense, they're kind of implementation issues, but in the real world, they actually consume, I would say, I spent almost as much time working on these as I did, like writing library of the system. So that actually implements the cryptography. So yeah, these problems are actually significant when you go to the real world. So this handling various item sizes, we've actually tried a lot of different ways with this because we've done it across 3 applications now. So the way we do this for Wikipedia is, in Wikipedia, we have articles that actually are quite different in size. So the smallest Wikipedia article compresses to like a very small size of like less than 1 kilobyte. And the largest articles like are hundreds of kilobytes. So the raw data is very unbalanced, we say, right? The items are not even in size. So the naive approach is to kind of just take the largest item and make that the item size, and then pad the rest of the items. So if you have 1 million articles, you just kind of pad all of them to not 20, but maybe 100 kilobytes, and then retrieve against that. And the problem with that is kind of obvious. There's a ton of wasted space. And wasted space, when that space is going into an FHE computation, is really bad. I mean, it would not only waste literal space in memory, but it will also make the computation much, much slower, because now we're processing homomorphically all these bytes that don't mean anything. So it's really bad to have wasted space for performance. So we kind of do what you might think of doing, which is we split the large items and we try to kind of pack the smaller items into a bucket size. So we chose a bucket size of 20 kilobytes, and then what we do is we take the small items and pack them, and we take the big items and split them. There are some little alarm bells you should go off here. So what kind of leakage are we introducing by, say, splitting a large article into two? Maybe the pattern by which someone retrieves large articles now is going to say something about which articles they're retrieving. So yeah, we have to think about that. We kind of have like a leakage model, and we try to minimize the amount of leakage we have from long articles. In some sense, some leakage is difficult to mitigate, but yeah, that's our first concern. The other concern is, okay, we've rearranged the items and split the large one. So, how is that rearrangement going to get communicated to the client? Because, originally here on the left, we said that the client knows, a number from 1 to 5 of the item that it wants. And now, if I want item 4, how am I to know that actually item 4 is no longer in the 4th position? It's in bucket 1, So that mapping, we've introduced some new data that the client needs to make a query. So for Wikipedia, this is actually not a problem. And the reason it's not a problem is, people expect autocomplete in Wikipedia. We can't offer just like, the exact name of the article that you want and we take you there. And so we have to download actually a list of all the article titles anyway. It costs a lot of data, but it's worth it, I guess, and it's cacheable. So basically, because of that, because we're already communicating all the article titles, it's actually no big deal to also communicate which bucket each article falls into. And so the Wikipedia demo, if you've ever looked at like the network inspector, it consumes a fair amount of network bandwidth because it's most of it is actually not for PIR, it's for all of this stuff. So yeah. There's another kind of model which has some advantages, which is basically using hashing to store the items. So if we take every item that we want to store, and instead of kind of arranging it linearly, we hash it, and we take, say, in this case, I've said, let's take the top 3 bits and make that the bucket. So, there's 8 buckets, and we take the top 3 bits of the hash, and, all the items with 0, 1, 1 as the top 3 bits of the hash will go to this bucket. Then what we get is basically the mapping is implicit in the hash function, right? So we don't need to communicate an explicit mapping about which items go to which buckets because that's just the description of the hash function. And it works as long as there's lots of small items, right? So the reason you want lots of small items is basically you want it so that if you randomly, the hash is essentially kind of randomly assigning objects to buckets. Basically, you want it so that if there's lots of small items, then you know that the variance in the size of each bucket is pretty small. So it's safe to kind of make the bucket size this way, and 4 or 5 standard deviations away from the mean, that the number of items in each bucket will not exceed this amount. It's actually a really neat trick because there's no mapping that you need to communicate, and it's easy to. It works really well when the items are all the same or very similar size, which comes up more often in applications than you think. For example, for ENS resolution and Bitcoin balance lookup, and this is kind of related to the classic like PIR with keywords kind of system, but it's just kind of explicitly instantiating it. Yeah, so, okay. So the second problem is this, okay, so that, sorry. Yeah, so the second problem I want to talk about is leakage. So the point of doing FHE-based PIR is to achieve strong privacy. What we mean by that is, we want to minimize metadata leakage, and normal apps are just not designed to do that. So in, our Bitcoin block explorer, for example, our goal is to, prevent the server from learning what the client's Bitcoin address is, right? But, a normal app that does this actually leaks this information in just like actually 10 ways, not just one way. So the first way it leaks the information is there's usually like a tracker, so there's like an embedded tracker that's actually like tracking every keyboard action and every mouse click, and all of that information is actually getting uploaded to a third party. So the first thing you can't do is you can't use an embedded tracker if you're building a kind of a strong privacy app. When you go to apply PAR to the app, you might notice that actually even the structure of the API calls makes it difficult. So, the way REST APIs work is like the item ID is literally in the URL of the fetch. The point of our system is actually that we want to hide that information. So we have to kind of change how the API is structured. We have to make everything kind of post requests, and we have to kind of not make the URL this identifying resource. It kind of goes against the fundamental principles of REST, basically, to deliver this. Concepts like logging in to a user account or just an identity at all in the app are leaky. So, they will correlate activity between accounts or between people. So even after you do the PAR part, it's hard. It's still hard. There's still more things you have to do to kind of not defeat the purpose of the PAR. And I'll just share some examples from our actual demos and apps and show, where this comes up. So the first one is that for Bitcoin balance lookup. So, something you might expect if you look up a Bitcoin address using our Explorer is you might want to see your Bitcoins in USD. This is like a very requested feature. This was like the first request we got before we had it. People wanted USD display. It sounds kind of simple, right? But we need to get the exchange rate. We don't want to get the exchange rate from a third-party API. And there's actually a huge, or there's a relatively large foot gun here, like a thing to stub your toe on here, which is, if you just kind of naively fetch the result and then in your client JavaScript, just, try to convert the amount and make the call to get the exchange rate to a third-party API, you'll actually leak some information, because you'll leak whether or not the query was successful. You'll leak basically if this page had instead displayed an error message, maybe that call wouldn't have gotten made, so you would kind of be leaking that information. It's pretty bad, actually. So you have to be very careful to always make the exchange rate call kind of independent of query success or failure. In fact, ideally independent of whether a query is made at all. So we're kind of careful to do that. Another thing, this is even simpler, you want to know when transactions happened, and the block number is not really informative to human beings. So seeing that the block that this transaction was in was 760031, it's not super useful. What I want to see is this time. I want to see 1 day ago. How do I get the mapping of block IDs to time? Well, we got to do kind of the same thing. We need to get a mapping that's oblivious, and we need the complete mapping. And we don't want to, kind of conditionally fetch the mapping depending on query success. So we also have to do that. Thankfully, that's not very large. It's like a couple megabytes, but it's still another kind of obvious thing you might accidentally do is kind of just make some API call there and then leak which blocks were in the which blocks contain transactions relevant to your address. So these are just kind of simple examples in the Bitcoin balance lookup case. I also have some examples for the Wikipedia demo. This is simple, but the articles can contain images in Wikipedia, and we're fetching articles from a server that we want to be secure against, even if it's malicious. So it's important that the client kind of make sure not to make any web requests dependent on item content. So it's important that the client strip all the image tags. In fact, to to kind of further mitigate this, we set a really strict content security policy, which is this kind of browser setting, or I should say page setting, that lets you kind of specify a specific whitelist of allowed origins to make requests to, and kind of block all third-party origins and actually block all image requests totally. If you want images in your private Wikipedia, you need to put the images in the database, right? You can't just kind of fetch them directly from the web. And like I mentioned before, yeah, for longer articles, it's important to make your request pattern for the subsequent chunks as like the user scrolls down. It's important to make that request pattern in some way not less likely to leak that you're reading a long article. All right, so this is the last problem. The last problem is explaining it. And by it, I mean PIR and FHE more broadly. So I think to everyone, including me, it's not intuitive that this is even really possible. So this is what makes me excited about the field, is that it's paradoxical, it's magic, it's cool, but it also means like our standard mental model of encryption is just not sufficient to explain and understand how this works. So when you tell people there's a private key value store, it's difficult to explain exactly what we mean. You know, it's difficult to explain exactly that, you know, truly the server could be arbitrarily malicious and still not learn your query. I think I am still learning how to explain that, especially because we have really been drilled in as developers, especially, that basically encryption is just garbling. You know, encryption just is this, the mental model we have is like, you know, regular stuff goes in and then the encrypted version is just, you know, gobbledygook. And, you know, then to say, actually the gobbledygook has a structure and, you know, you can do computation on it. And then when you decrypt, the computation got applied to the plaintext. It's actually kind of a weird thing. So we faced a fair amount of difficulty just kind of explaining that. The other thing that I think we've hit with PIR especially is it's not intuitive which kinds of problems are easy and which kinds of problems are hard. So I'll give you an example. You know, what's hard is doing full text search. That's hard. You got to tokenize all the input. You got to scanning it. It's tricky. It's very expensive. Private push notifications is a request we got more than once actually. You know, it's push notifications are inherently, you know, they leak a lot through timing, right? So this is not a situation where PIR is a great fit, because PIR is all pull based, and you need to make your pulls on some kind of either regular cadence or you need to hide, you know, when a message was delivered, because of course when a message was delivered is really sensitive information. So push notifications and PIR don't really go together very well. And then, you know, another thing that's really hard, especially in the cryptography, in the blockchain space, is, you know, people are really excited about ZKPs. I think, as has been said before, you know, ZKPs are like where FHE was maybe, ZKPs are where FHE will be maybe in a couple of years. But, you know, doing zero knowledge proofs over homomorphic computation, it's definitely still in the, at least from our view, in the realm of, you know, kind of research. We're working on it. It's getting better, but it's difficult. And so, you know, someone will just be like, "Oh, we'll just zero knowledge proof over that." Yeah, give us a couple years. You know, give me a couple PhD students and some time. Maybe someday we can figure that out. You know, what's easy is also non-intuitive. So what's easy is it's actually not. Today we can check membership against huge sets. So like if you have an item and you want to find out, is it in this set of 1 billion items that I hold? That should be, you know, quite cheap and quite fast. It's very similar in speed and difficulty to like looking up a Wikipedia article. In fact, it's slightly easier, I think. The set is smaller. So, you know, checking membership against a set of 1 billion items, it's not intuitive that that's easy, but it is. We can do that today. Doing lookups by hash, just like taking every transaction that's ever been recorded in Bitcoin and letting you look it up. It's actually, again, not that hard. That's super feasible. If you're willing to pay for the storage and the computation costs, it's absolutely feasible with the schemes and the constructions and even the code that we have today. And another thing that's easy that's not intuitive is it would be easy to slot your database into having data from more than one blockchain or more than one data source. So like I could make the database have half Wikipedia articles and half Bitcoin addresses, and every time you make a query, I could not know, whether you're looking up a Wikipedia article or fetching the balance of a Bitcoin address. And there's no real roadblock there. I mean, you have to choose your parameters a little differently. You might have to think about the mapping a bit, but that is feasible, again, today quite easily. So this difference between what's hard and easy, this is very hard to communicate. We've had to do a lot of kind of very manual communication about like, yeah, you can't do that, but you can do this. So it's a new design space. These things are bound to happen, but yeah, that's the problem we're facing. Our strategy is what everyone does, I guess. Write blog posts, give talks like this, and hopefully eventually I think our long-term solution is to build reliable services and good documentation. So what we want is to say, okay, here's the tool that you have. Let's make the tool really easy to use, and then let you figure out, how to apply the tool to your particular problem. And I think that is a kind of fruitful, that's the way we see FHE becoming useful most immediately. Okay, and I'll kind of wrap up now, but I'll just say a little bit about the future. So what's next for us? We're trying to open up this key value store that we built to build these 3 kind of apps, and we want to see what people build with it, and we want to help people use it, and we want to make it reliable and kind of operate at scale, where we're interested in seeing what happens when 1 million PIR queries are coming in to your service. We would like to get there. This service will basically let you store arbitrary data and then perform private retrieval from the key on it. If you want to try it out, email us. There's also a private beta sign-up form on Twitter and website. We'd love to talk specifically with you about like a particular application you're interested in. I think especially at the beginning, we're interested in applications that have commercial impact, but also in applications that are kind of public goods. So things like password checkers or password leakage checkers, like have I been pwned, or Wikipedia. These are things maybe that will not make a ton of money or something, but we're interested in operating kind of in a public good way that we could learn from and build like knowledge of PAR and FHE through. And I think in the long run, we're also interested in how could we make this a little bit lower layer, a little bit more of a concern for the technology stack and less a concern for people. So we would love like a standard that it does not commit to a particular scheme, because as we all know, the schemes change every so often. But we would like a standard that at least formalizes, this is the protocol for making a private query, like what is the PAR equivalent of a post request? I think that is something that we will need to make privacy preserving apps actually feasible to build for regular developers. So yeah, anyway, that's it. Thanks so much. And I would love to answer any questions you guys have.
Thank you, Samir. Thank you. This was super interesting. So we have a few questions here. Maybe I'll start with one question. So what are you currently using in terms of FHE scheme to actually do the retrieval?
So we use Spiral,
Okay.
big surprise. We for batch queries, there's a really cool work from Henry Corrigan Gibbs and Alexandra Hendiger and a couple other people called simple peer and double peer. That work is great when you make many queries against the same database. So we're currently implementing that for larger batch queries against a more static database.
Okay, I see. And so you don't do any kind of I would say you're not computing formulas on their range of value, right? You're just retrieving the index that you fetch client side. Is that correct?
Yeah, it's a lot of smoke and mirrors behind an ultimately simple kind of retrieval of just like, I just want this item at this index. Yeah.
Okay, and do you think that the same protocol could work if you wanted, for example, to retrieve the first element that satisfies some condition, right? I don't know, maybe XYZ numbers between 5 and 10.
Yeah, so I think the most promising way to do that is it's still a little bit researchy, I think. I think it gets difficult whenever there's any kind of like computation more than just like multiply this one by this, plain text value. But the best cool work that is actually practical today is the oblivious message retrieval paper from Zayu Thomas and yeah. That paper for which does a demo for Zcash, that is where they actually do a fairly complex operation. They do a public key test for every message as to whether to retrieve it. So I would say that is feasible. But even there, if you look, they did not start with a query that they want, like a range query or something, and then design. They actually started backwards. So they started from the public key. They started from the premise that like everyone would produce a tag of their choosing, and then perform the computation. So they optimized that tag to be decrypted homomorphically very efficiently. So it really helps to have co-design here. I think doing like an arbitrary, like I'm going to take your random SQL table or your random database table and just make it homomorphic, that is, I think, still quite hard in my opinion. So.
Okay, understood. Cool, thank you. For those of you who have questions, just unmute yourself and ask them directly.
Yeah, sorry, I didn't realize I didn't have the chat open. I didn't realize there were so many questions.
Christian, maybe you want to ask your question?
Yes, thanks for passing the mic around. So thank you for our presentation, very interesting. I was wondering, but already someone responded and it's pretty valid, the response. My question was if you are leveraging mixnets, you can do the third-party APIs call, but then I saw the response that you should trust at least one node. So basically it kind of already responded, but thanks for the presentation.
Yeah, I think that's accurate. I would just add, like, you need one trusted node and you also need a bunch of nodes. Like, there have to be many to make it work,
Yeah,
so again, it's kind of more that differential privacy thing where you're hiding who you are in a set. This is more like I want to hide the content of my query.
Yeah, it makes sense. It's a different threat model, indeed.
Yeah.
Thanks.
Okay. Arvid, do you want to ask your question?
Sure. Yeah, I think I realize the answer to this, but how do you fetch a transaction with a given hash? Are you doing the thing where you take the first few bits, or?
Yeah, we're doing the thing where we take the first few bits. The good news is transactions, again, are also small, and the item size in PR is much bigger than a transaction. So we just kind of can randomly bucket them, and they come out pretty even. The min max is like they're all like between 18 and 22 kilobytes. So we just set the bucket size to 24 and call it a day.
Makes sense. Thank you.
Do we have any other questions? Okay, maybe I have just one more question on my side as well. So to understand a little bit of how this could be deployed as a product, as opposed to you having to build every use case, what would be necessary? Like, what can you factorize for, like, what is like the standard model for what you're trying to build here, basically?
It's a great question. That's a deep question that we're trying to answer. So yeah, so I think there's two ways that we can factor out a lot of work and remove the expertise you need. The first is this key value store. So I think that if you imagine it as like, this is Amazon S3, except you can just like retrieve some keys privately, or yeah, retrieve all the keys privately. I think that's a mental model that's much easier to communicate to people, and it's useful. So like we build all of our demos using that, like we basically underlying all of these is a single kind of software stack that it amounts to this key value store. The second way is honestly, I think there's a whole avenue of kind of, let's call it pre-baked APIs. So that is kind of like, I want to take my messaging app and make the contact discovery private, right? That's the first thing is key value store. But there's another angle, which is like, we can offer a kind of already baked API that shows you Bitcoin balances, and it lets you do private retrieval. And we will do all the data processing, and we will kind of simplify all of that. And at the end of the day, you download our client and make a query and get the balance, and you don't do anything else. You don't worry about anything about really how it works. It's totally, there's no setup, there's no,
Okay, so any key value store type of thing. And so how would you accommodate with large entries? For example, you talked about images, right? They're going to be probably bigger than 20 kilobytes. How do you retrieve like a 5 megabyte or 100 megabyte piece of data?
It's a great question. So there's actually, I would say two things there. So one is, you might think like, I know when I started this work, I assumed that, text was easy and images and video would be like really hard, like video would just be like crazy. But it's funny how, it's really not. It's actually the main costs associated are actually more the number of items than really their size. So I'll give you an example for video. It's really quite effective to just partition the video into, say, let's call it 10-second increments, and just do retrieval on 10-second increments of the video repeatedly. The other thing I'll say is, our work introduced a thing that I think most people do, most subsequent work also does, which is select the parameters based on the database size. So we don't just like ordain 20 kilobytes. For the particular application, we'll select the parameters. We'll update them as the data changes. These are all the kinds of things we want to abstract from you. So if you wanted to download, a PIR scheme today and use it, you need to do all these things. You need to think about what the parameters, you need to think like, what is the plaintext modulus, which is a crazy thing to ask, a normal kind of developer. So.
Okay, and so if you wanted to retrieve multiple responses so key value store, so it has to be only one value per key, right? So you cannot have, so you cannot, for example, say retrieve all the values that start with ABC.
Yeah, that's not possible. So it is definitely exact lookup. It is like, give me your key, I'll give you a value. But I think that I guess again, the problem we're solving is much more limited than the castle of things that are possible. You and I both know it's possible to do like really cool, crazy stuff. But I mean, by forcing ourselves to kind of focus on the things we can do today efficiently and at a fairly cheap cost, I think we can make some progress. That's our thought.
Okay, great. Okay, well, thank you very much, Samir.